Hi everyone, my name is Arjun, and today I will be discussing our work on contact transfer, a direct, user-driven method for human-to-robot transfer of grasps and manipulations. Efficient and robust computation of feasible grasps and manipulations is a long-standing problem in robotics. Historical analytical works employed physics-based reasoning with forces and torques, while recent data-driven works endeavored to pose-match joints from images or motion capture. But the often single-point approximations of the former and limited motion coupling of the latter typically oversimplify hand-object interactions, which often involve large areas of contact. Consequently, a growing body of research has aimed to use contact areas themselves as the basis of grasp generation. The results are compelling, but the caveat is that these techniques rely heavily on ground truth priors or expensive grasp sampling, which limits the generalization, speed, transparency, and flexibility of the approaches. Instead, we advocate for a direct approach of mapping corresponding contacts between objects and hands based on the key idea that contact areas are preserved regardless of the projection surface. Intuitively, if you press your hand against an object, the same contact shapes would form on both surfaces. But if we only have object contacts on a target hand, we need to somehow generate hand contacts in order to produce the mapping. And even with the mapping, we still need an efficient means of computing joint-space grasp solutions. It's not yet clear how to do either of these, but we'll dive into them in the remainder of the talk. Fortunately, we can directly transfer contacts between surfaces provided we choose a robust cross-domain surface parameterization. To do so, we first parameterize the contact in polar coordinates, and then exploit the logarithmic map surface parameterization of Schmidt et al. To decal the contact onto arbitrary surfaces. Our transfer process is similar to peeling a contact off of one surface and sticking it on another. And as we demonstrate, selecting the transfer parameters is intuitive. All you need to do is align the source tangent vectors on the two meshes and select the corresponding hand source point. Transferring the contacts can then be done in milliseconds, providing an as isometry preserving as possible transfer. But what we ultimately want is the best hand joint space solution that can match these contacts. If we've already done the mapping work, it would be nice to just hit a button and get a solution. This is exactly what our optimization approach aims to do. To do so, we consider three objectives. Obviously, we would like to bring the matching contacts as close to one another as possible, but we would also like the hand to conform to the geometry of the object, hence the inclusion of both the distance and normal terms. The third term, which we call the prior, captures flexibility by discouraging deviation from a rest or user-edited pose. Importantly, the prior in this case refers solely to the existing hand state, not externally sourced ground truth data. Throw in some weighting coefficients and joint limits and out pops our straightforward three-term optimization formulation. Our objective is both fully differentiable and extremely cheap to compute, which means we can find solutions even for high degree of freedom hands in sub-second timeframes using fast gradient-based solvers, even in response to shifting objects, until we arrive at a solution that is suitable. But despite its simplicity, our method is adaptive to user feedback, robust to poor initialization, and can handle hard-to-reach contacts. Our method can deal with widely differing hand and surface geometries for computing high-quality, kinematically feasible static grasps. And when combined with our contact tracing framework, we can even rapidly keyframe out full manipulations. Finally, we show that the computed solutions do produce reasonable behavior on a real robot hand. In summary, our method provides the first direct, intuitive method of transferring contacts between arbitrary surfaces. Our process is straightforward, fast, and provides intuitive solutions with transparent behavior. But there are drawbacks, including that we don't yet consider contact dynamics and still require knowledge of meshes and user input. Our next goal is thus to improve the autonomy and physical plausibility of our process while striving to maintain fast performance. Thanks for listening.